It's time to talk about the role of F-tests. F-tests allow us to show whether the population variances are equal. And when they are, we're allowed to pool our sample means. And that gives us a simpler test. Now, I should say right now that you do not need to use these simpler tests. In practical terms, the only difference is a slight change in the p-value. That said, we're now going to work through an example where we do perform an F-test to check to see if we can pool the sample means. To do that, I've copied the data, 2 columns for the beef and the poultry hot dogs. Let's go into a GeoGebra spreadsheet and paste that data in. It looks like we got all 20 of each. We're now going to determine whether the data is normally distributed, and to do that we need to look at each set separately. So let's do one variable analysis on column A. Here's a histogram. It certainly looks skewed to the right, doesn't look symmetric, but we'll now check a box plot. We're checking for outliers. It looks like it would show us an outlier if there was one. There are no outliers. Let's now look at the normal quantile plot, and the data looks very closely aligned along the line. So the first set of data, I think that was the beef hot dogs, looks like it is perhaps normally distributed. Now let's look at the poultry hot dogs, the second set. Again, let's do one variable analysis on it. Let's look at a histogram, and that certainly looks curious. Not bell-shaped in the least. There's a big gap in the middle. It looks like randomly distributed peaks compared to a normal distribution. Now let's look at a box plot. No outliers. And then the normal quantile plot, and the data is spread around pretty far from that line. So it looks to us like we can conclude that the second set of data may not be normally distributed. So we remind ourselves that a t-test for a difference of means is fairly robust, but that our results may not be accurate. Okay, now let's do 2-variable analysis. Let's look at columns A and B, and let's see what we have. And now what we're going to do is determine whether we have to not pool or whether we're allowed to pool our data when we go into the difference of means. So just as a kind of preview, when we do that, we're going to be asked whether we can pool that data. So I'm going to copy the standard deviations for the samples, that is the S for this first column. Remember the sample was 20 for that, and I'm going to go into the F cumulative distribution function. So our first sample had a size of 20, and let's plug in the standard deviation. Oh, that's a lot of decimal accuracy there. And let's, my goodness, that's a humongous amount. Something went kind of wonky there. So let's go back in and copy that again and see if we got it this time. Looks like we got it this time. So there is our standard deviation. We need to make that into variance by squaring it. So we'll do that. Now let's remind ourselves that the second sample also had size 20. So we'll put that in. Let's get its standard deviation. Let's plug it in. Let's see if that worked. It looks good. 81.17856. We need to square that to get variance. And it looks like our F value is approximately 16%. Let's go back to the workbook, and we can remind ourselves that what we're looking for is whether the probability that that F test is at least as strong as 5%, that is greater than 5%. And it looks like we've got about 16%, and that means that we can use the simpler test. That means that we can pool the sample means. So when we go back to that t-test, we can pool those sample means. Now, before you look at the p-values and the t-values, let's remind ourselves that this is a test, a hypothesis test. We've got the null hypothesis, but we also need the alternative hypothesis. So let's go back to the text itself. And it's, well, actually, before we do that, let's remind ourselves of the means here. So it looks like for the first sample, the mean was 401. For the second sample, the mean was 450. So it certainly looks to me like there's less sodium in the first sample than the second. So let's see if that agrees with what our text is asking. Is there sufficient evidence to show that beef hot dogs have less sodium on average than poultry hot dogs? So here's beef in the first, and it's asking that us to check a hypothesis test whether that's actually less than the amount of sodium in the poultry hot dogs. So first column, less than second column. Let's see what that means here. So the first sample less than the second sample. So mu1 is less than mu2. That is, the first mean is less than the second mean. So when you subtract a larger number from a smaller number, you get a negative. A negative number is less than 0. So let's make sure we've got that correct. And now we've got our p-value, our t-value, and of course our degrees of freedom. We've selected pooled. Now, just as a point of interest, notice that if I disselect pooled, the p-value only changes by a very, very slight amount. Let me do that again. And you can see that it's in the, tenths, hundredths, thousandths, 10,000ths place that difference occurs. The degrees of freedom also changing. Let's leave that pooled. That's why we did the F test. Now our p-value is 0.05075. Boy, just a tiny bit more than 5%. Let's see what that means for our question. So let's go back to the text. And it says check at a 5% level of significance. Well, we're pretty darn close there. So let's remind ourselves that when the p-value is greater than alpha, we're going to fail to reject the null hypothesis. There is not enough evidence to show that beef hot dogs have less sodium than poultry hot dogs. And remember, we were not convinced that the data was normally distributed. So we do realize that many of the assumptions are not valid, so this interpretation may also be invalid. A quick reminder, we copied the data into GeoGebra. We looked at the data separately to see if it looked like it was normally distributed. The second set of data certainly did not. We then did an F test using the standard deviations given to us when we did the t-test with the difference of means. We had to square those to get variances. That gave us a p-value of 15%, well, actually closer to 16. That's more than 5%, so we were allowed to pool those. We then noticed that both the data and the question asked us whether mu sub 1 is less than mu sub 2. We wrote that as the difference. And then we got our p-value, we compared it to alpha, and we made our conclusion.